Hello and welcome back. By the way, if the sound quality is ever not what you'd expect, please just let me know. Alright, so I'm going to trace this triangle and the marks because the marks tell me what sides they correspond with. So I see this double angle. I'm going to take this double angle to this double angle, double arc angle, so B to S. Hopefully you played around with this a little bit. Okay, they're not lined up. So rotate around B until, a side lines up. BC is with ST, and then reflect over BC. Ta-da! Congruent. Use tracing paper to find a sequence of transformations that will show whether or not these two triangles are congruent. Done. List your sequence. Take by translation. Point B to point S. Once the whole triangle, we say translate the point, but really translation translates everything. So we're translating the entire shape over there until B is on S. Rotate around S until segment BC coincides with segment ST. Reflect over segment ST. Hey, they did something different. They translated until A was with R. There's that word coincides. Rotate. Oh, they say rotate the segment, but I see it as rotating the whole triangle until these two lines. So they picked a different point. Then they reflected the triangle. Great. We can use the word coincides when we want to say that 2 points or line segments occupy the same position on the plane. When making arguments using transformations, we will use the word a lot. Now the question is, how do we know that point C has to land on point T after the reflection, making all the sides and angles coincide? Answer this problem as best you can to justify why ASA criteria guarantee that two triangles are congruent. It may be helpful to think of how you know point C can't land anywhere else on the plane except on point top of T. Okay, so what they're talking about is this moment. Okay, let's do it their way, I guess. A to R, rotate until bing, and then reflect. Now they're saying C lands on T. How do we know it does, though? Sure, it looks like it does, but how do we know it must? Well, what they want us to focus on are these. So, in other words, this other triangle has the same length there, we know because of the mark. So these two angles are the same distance apart. Also, the angles are the same. So, when we flip it, these sides, which are straight, extend until they cross. And there's nowhere else they can cross because the angles are the same distance apart in both triangles, and they're pointed in the same direction in both triangles, which means they're going to finally cross at the same spot in both triangles, and when you reflect over there, this is the only place that the third point can be. So C must land on T. Okay, this gets at the heart of the rest of this unit and gets to the heart of lots of geometry, which is triangles and how we can know that two triangles are the same, congruent, without having to know everything about them. And that's because triangles are limited. Every point is connected to every other point. This point connects to that one and that one. This point connects to that one and that one. This point connects to that one and that one. They all touch each other. Same thing with the sides. This side is connected to both other sides. Everything's connected. There's not a lot of degrees of freedom in this triangle. And so just knowing an angle, the side, and the next angle, that locks in the triangle because there's only one spot that those two sides can cross now. And if there's another triangle with the same corresponding angles, maybe this is 50 degrees, 50 degrees, 60 degrees, 60 degrees, maybe this is 10 feet across, 10 feet across. Well, if we had two triangles with those ingredients along one side, well, then there's only one spot that they can meet. So these two triangles have to be congruent without even knowing what's going on in their top. Their tops are locked in by the information we do know. Okay, but what if we knew a different situation? What if we knew two sides and the angle in between them? Now we don't know two angles. Remember, last time we had two angles, which meant that they had to point to the same spot. But now we have only one angle. Is that enough information to lock it in? So given criterion, we have two congruent sides and the angle betwixt. That's an old-timey word for between, but it just makes it fun. Are the triangles congruent? Let's find out. K to Q. Rotate until single mark on the single mark side line. Flip over QR or reflect over QR. Ding. Single mark. Yep. They are congruent. List your transformations in order performed. No, we did point to point, side to side, flip over that side. If the triangles are congruent, justify why this will always be true based on this criterion. Based on the criterion when you have two congruent sides and the angle between them. Will it always work? Well, this one's even actually more straightforward than the last one. Basically, if you have two triangles, and you know this angle, let's say it's 40 degrees. And you know this is 10 feet long, and this is 7 feet long. So there's the thing where we have side angle. This is called side angle side. Whereas the last one was called angle side angle. So now we have nicknames for our situations. This situation's nickname is ASA. This situation's nickname is SAS. Both situations, turns out, are enough because now there's nowhere for this triangle to go. The distance between here and here is locked in. And also the angles are locked. There's only one piece, you can only put one piece of edge here, and it'll be identical. And it'll also lock in these angles as the same. Let me do double arcs for those. And here I'll do arc with a mark. Okay, and this will be triple mark side. Okay. Congruent. Whoa, what's going on with this congruency symbol? Okay, moving on. Okay, now we have the situation where we have three pairs of congruent angles. We know three angles. Looks like Q matches with, or sorry, O matches with Q, U matches with R, I matches with P. Let's take O to Q, spin until QP, or OI is on QP. Uh-oh. Flip, you see, this isn't gonna look good. Flip over. Yeah. So I can get part of the triangle to match, but not the whole, part of it's always sticking out. One side, now we can double check that these angles are all the same. Let's zoom in.
Mr. Kelly, could you please come to the main office?
So
Mr. Kelly, to the main office.
they weren't lying. This angle matches this angle. That's true. Here, they weren't lying. This angle matches this angle. It's true. And they weren't lying about this angle either. This angle matches this angle. But the triangles are not congruent. So even having all the same angles is not enough. Also, no, I'm not listing those. If the triangles are congruent, justify why this will always be true. They are not. Okay, we will discuss the next one, where you know an angle and a side, or should I say side angle, in part 3. This is a big lesson because this is a huge topic in geometry, triangles and matching triangles together and how we can prove triangles are similar so that we can build stuff and know for sure it's correct.